First thing I'm going to start off with is taking the derivative. So I have this function, and some of the pre-cal is going to help you out. If you know what this looks like, you can kind of graph this polynomial right away a little bit, but we don't need to do that. We could just go straight to the calculus and save ourselves some work. So I find the derivative of this is going to be 4x cubed minus 6x squared. That's the first derivative, and then I'm going to do the second derivative right away because it talks about in these choices there's inflection points. So we'll go over the definition of an inflection point in case we forgot, as it is that we do this. So here's the second derivative. And what I'm going to do now is I'm just going to draw a number line. I'm just going to go and I'm going to have some straight line, and I'm going to mark out some key points. So we have here, if you look at my first derivative, I want to solve for when my first derivative is 0. That's when the slope of the tangent line is 0, or when it's horizontal, when the tangent line is horizontal. So I want to see where those values actually occur. So I set this equal to 0, and I solve for x. So if you look, I can factor out an x squared, and I'm left with 4x minus 6 on the inside. And there's essentially two values for when I'm going to have a horizontal tangent line at x equals 0, and then the other value is whatever value makes this factor equal 0. So when is this factor equal to 0? When x is 3 over 2. And take your time and be sure that you solve this correctly for these two x values. And I'm going to mark off these points. So 0, and let's say this is 1, and this is 2. 3 over 2 is right here. So I have these values marked off. These are critical values because they make the derivative equal 0. Now I'm going to determine what's happening, because extremum occur if the graph goes from increasing to decreasing or decreasing to increasing. So if f is decreasing, 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 and then it begins increasing, 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 this is a relative extrema. Okay, this is a relative min, right? And that's part of some of these questions are all involving relative extremum, and then there's inflection points, which has to do with the second derivative. So let's see if I could first get where the relative extremum are with the first derivative. So what you do here is I have these points marked off where my derivative equals 0. This is the point 3 over 2, and then this is x equals 0. These are my relative, these are the points that make the derivative 0, which are critical values, we call them, or critical points, whatever. Let's just say where derivative equals 0. Where f prime of x equals 0. And what you want to do is you want to pick test points. Okay, so anything in this interval to the left of 0 is a good test point. So for example, -1 is a good test point. You plug that into your derivative, and if your derivative is negative, then your function is decreasing all the way up to 0. You can guarantee that. So let's see what we have here. So if I plug in -1 into this function, right, if I factor this function a little bit, x squared, 4x minus 6, if I plug in -1 to x squared, it becomes positive. This factor over here, x squared, is always positive. So it's a positive times whatever I get here. What happens when I plug in -1 here? I get -1 minus 6 is -10. So that's negative. Positive times a negative is negative. That means that my function is decreasing all the way up to 0. Now you want to determine what's happening to your function between 0 and 3 over 2. So you pick any test point. And a good test point could be 1, because 1 is between 0 and 3 over 2. I plug it into my derivative again. 1 squared is just 1. 4 times 1 is 4 minus 6 is -2. So it's negative still. So what that means is that what happens here is the graph of f. So what I'm going to do in orange is the graph of f what happens here is that the function comes down, it's decreasing, 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 and then it completely flattens out and then continues to decrease and decrease and decrease and decrease. And now I want to see what happens again now at 3/2. So it flattened out, so the slope of the tangent line right here would be 0. So that tangent line is indeed horizontal at that point 0. So this point right here is not a relative extrema, this is 0. But let's see what happens at 3/2. So again, pick any point to the right of 3/2 and plug it into your derivative so you get a sense of what your function is doing. So like 2. If I plug in 2 here, I get 2 squared. That's obviously positive. 2 times 4 is 8, minus 6 is 2. I get positive. So my function is increasing all here. So it switched signs, and that means that there's a relative extrema right here. So here's one relative extrema. Relative min, to be precise. So there's one relative extreme, so it's either this one. Oh, and then there you go. You already know. Just from that, your choice is C, and you don't even need to worry about the other ones because it's the only one with one relative extremum. Now you could do, just to be clear, and you'll see that there's going to be 2 points of inflection, and let's go over what that means, even though we know our answer for this one. So let's go over what 2 points of inflection can guarantee, or how we could find out that this function does indeed have 2 points of inflection. That involves using the second derivative. So a point of inflection is going to be where the function goes from concave up. So concave up looks like that, and then concave down looks like that. Now the point of inflection is where it goes from one to the other. So like, look at this curve here. So over here, this curve, look, there's going to be a dividing line, right? There's going to be some point where here it's concave up, right? So to the left, this function is concave up here. And then over here, you should see that it's concave down. And this point right here is your inflection point. Okay, now let's look and see. And the second derivative is going to tell you where your inflection points are, because you set your second derivative equal to 0, or where your potential inflection points are. So I set it equal to 0, and I'm going to factor out the 12x. I'm going to be left with x minus 1. And then I set it equal to 0. It gives me x is 0 as a possible inflection point, and x equals 1 as a possible inflection point. And again, I mark off these points on this curve here. So let me do it in a good color that we have yet to use. So let's see, I have x equals 0. This is a possible inflection point, and then x equals 1. And I do this same game, but now for the second derivative. So for example, I'll plug in -1, but now into the second derivative. So -1 into the second derivative gives me a negative times a negative, because -1 times 12 is -12. Then -1 minus 1 is negative. Negative times a negative is positive. So my function is concave up all the way to 0 because the second derivative is positive. Concave up means f double prime of x is positive. So my function, and the way I drew it, is also that it's concave up. Then now let's go to this part right here after 0, between 0 and 1, because the point where my second derivative is 0 is at 1. So now let's see what happens at this 0 value. So between 0 and 1 is a half. So a half times 12 is positive. A half minus 1 is negative. So it would be a positive times a negative in this case. So it's negative. And if you look, my inflection point being right here at 0 makes sense because it was concave up and then it's sort of concave down all here. And if my second derivative is negative, it's concave down, all there. And then now let's see what happens after 1. So like 2 is a good example. So 2, I plug in 2, and my function is concave up. If you plug in 2 into your second derivative, you will see that it's positive from here on in. So how many times does it switch? And those will be inflection points. So it went from positive to negative at 0. That's one inflection point. Then it went from negative to positive. This is another inflection point. So there's 2 inflection points, and C is now even further confirmed.